Okay, yeah. So Janet asked me to give a brief introduction into the methods, and into, let's say, the challenges arising from applying bias adjustment. And my talk is about univariate methods, and it's about standard methods which are broadly used. So there might be some very sophisticated methods, and I may tell you about these, which are not widely used. So I basically don't cover them, but I would just mention that they might be some workaround or so about, for some problems. And then later, Mathieu will talk about multivariate bias adjustment. So he will basically build upon what I talk here about, these simple methods, and then he will go to the more complex ones. Okay, so when we want to assess changes in future climate, we use climate models. So, for example, GCMs here. So this is from the 2013 IPCC report, global mean temperature projections. And these models, these GCMs, they have biases. So, for example, when you look here on the left, on the multi-model mean CMIP5 model biases in surface temperature, you see that, well, in many regions, the biases are relatively small, within 1 degree. But then you see specific regions where this is much, much bigger. And like here, for example, over the North Atlantic or over the oceans here, you might say that this is not so relevant for you because you're not interested in the oceans, but these biases, of course, have knock-on effects on other regions. And when you look at precipitation here on the right-hand side, so that's the relative error in percent, you see that these errors also over land might be substantially bigger. So in some regions, you've got really, really high biases that it's too dry, or in other regions, you are too wet. And what you can, of course, do is you can downscale your GCMs, but also these GCMs have biases themselves. So this is from a paper of Sven Kotlarski, where they looked into Eurocortex models with so-called perfect boundary conditions, so driven with a reanalysis. And here is the observations for December, January, February, so the winter season, and here for the summer season down there. And then you see 9 individual models and their deviations from the observations. So it's quite substantial. So a couple of degrees in some regions. And here you see the same thing for rainfall. So this is relative errors. And in some regions, the relative errors might be 100% for some of the models. So that's the one thing. And the other thing is these models have a coarse resolution. So this is a typical GCM. I mean, that's from the AR4, but I would say this figure here was not really from an operational GCM back then, but more of the very, very good ones. So this is more state of the art nowadays. And you see that, yeah, when you're interested in a, I don't know, in a small region somewhere in a country, then yeah, your model will not really resolve the regional processes there and the topography. But even if you downscale with an RCM, you still have resolution issues. So this yellow area here, that's a typical RCM grid box. They might be a bit finer by now. And you see the the topography here so that's somewhere in the Alps. And the topography is, of course, much more complex than an RCM grid box. So you don't see the mountain peaks here, you don't see the valleys. And these two issues, they have got consequences for impact modeling. So this here is just, well, just to illustrate, you don't need to understand the details here, but it's a hydrological model driven with climate model or observational input, and over a couple of years. And basically the goodness of fit here tells you how good the hydrological model then represents reality. And when it's driven with station observations, that's up here, you see it works very, very good. Then when you take a standard regional climate modeler, for example, here, the performance is very, very bad. But when you adjust the model, the performance gets much, much better of the hydrological model. So you want something that ideally both downscale. So here this shading is from a statistical downscaling method, and the line is from the RCM. So and adjusts the biases in your models. So basically we've got oh, I need to get rid of that one. There are basically two approaches. One is bias adjustment, and the other one is statistical downscaling. And many people talk about them as if they were the same. So in particular, when you go to the literature from the United States, when they talk about quantum mapping or similar methods, which are essentially the same as quantum mapping, they call this statistical downscaling. But I will give you a couple of examples to show that this is not the same thing. And when you use bias adjustment for statistical downscaling, you may run into problems. Okay. So let me first introduce a couple of methods. So just really standard methods. And before we go there, I think we should clarify what we mean by a bias. So in statistics, a bias for a certain parameter, yeah, let's call it theta for now. It could be the, I don't know, summer mean temperature. It could be winter rainfall or whatever. Or it could be even the 95th percentile of heavy precipitation. Yeah. So that's one let's say a statistic. Okay. And the bias is basically defined as the difference between the true parameter and the expected value of the estimate. So and we can think about this as our model simulation, and this is the observed truth. And we have and a key thing between here is that we have got expected values, and we're talking about a true value. And this is a bit an issue now, because we are talking about systematic discrepancies between model simulations and observations. So when you have just one time series of a model and one time series of observations, and you calculate the mean of both, then you've got estimates of both. So in reality, we always only have estimates of biases. So internal variability of the climate system basically makes these estimates quite noisy. So our bias estimates might not be very good, and this might have consequences, for example, when it comes to when you calibrate a model to a certain period, and then you estimate, let's say, the climate change signal, you might get something else when you take a different realization of the model, or when you take a slightly different reference period. You might end up with different climate change signals there. So we have to keep that in mind. Okay, so the simplest models, bias adjustment models, are just adjusting the mean. So you could, for example, for temperature, you say, well, the corrected time series in the future, yeah, is the simulated time series in the future minus the bias, and the bias is then an estimate only, and it's the mean of the mean of the simulation minus the mean of the observations. So you would basically take, let's say your model simulates a temperature of 25 degrees, and you know the model is on average 2 degrees too warm, then you would subtract it. So instead of 25, you would get 23 here on this side. So that's the simplest thing you could do. With rainfall, you typically consider relative errors. So you would, instead of differences, you would take ratios, but essentially the same thing. So your model is, let's say, 20% too wet. So you rescale it by these 20%. Okay. A more sophisticated model for bias adjustment is the so-called quantile mapping or quantum mapping, where you basically do this correction for every quantile. So quantiles, I would assume that you know that, but just quickly. So it's basically when you have got your probabilities between 0 and 1, and your 50th percentile, yeah, that would be the median. Yeah, so so you would do a different correction for the median, or for the 5th percentile, or for the 95th percentile. That means for the low values and for the very high values. And so what you do is you basically define a transfer function. This is this one here, which gets you then a corrected value. And I will show you this on a figure in a second. And this transfer function can be empirical. That means that you really, in a way, look at the empirical quantiles and look at the the observed, or the quantiles of the observations and the quantile of your models, and then you define a mapping between each quantile. Or you assume a certain parametric distribution. So you could, for example, assume a normal distribution for temperature, or you could assume a gamma distribution for rainfall, or you could even have a specific model for extreme values. So there are many, many different variants of these. And one way where they might differ is, for example, in the way they adjust wet day frequencies, whether they can make can transform rain days into dry days or dry days into rain days. And then the other issue where there's also substantial variations amongst the models is how they deal with extreme events. So how do you correct an extreme which you have never observed? You don't have any, haven't got any observed quantiles there, so you have to, in a way, extrapolate. And you could use a parametric model and just extrapolate from that parametric model. Or you could assume that beyond what you've observed, the correction factor is simply the same. Okay, now let's have a look how this works. So here you've got observed rainfall. Let's say it's daily rainfall over some place. And here you have got simulated rainfall. That's what your model simulates. And you see the model simulates, for example, too many wet days here, and it simulates too low intensities for high extreme events. So when observations tell you it should be something around 25 millimeters, then the model tells you, well, it's just 15. So you don't want this, of course. So what you do is you basically shift everything up, and you could do this via a transfer function here. So you would assume a gamma distribution, for example, and then you would map everything up here. Then your values wouldn't perfectly fit. You could also do it empirically. That means you move every value up here, up here, up here, up here, up here. And if you get a new simulated value in the future, which is somewhere between here, then you would just linearly interpolate and move it up there. So that's the different possibilities you have. This here, of course, is not so noisy as if you do everything here empirically. Okay, now I talked about downscaling bias adjustment. So a climate model, let's say, has a certain resolution of, I don't know, 25 kilometers or whatever, or 12 kilometers, depending on what kind of model you have. And then you've got observations, and the observations may be gridded, like here, maybe at the same resolution even, or they may be at a finer resolution or even to the point scale. So I've got a station somewhere. And you have then two different settings. If you apply a quantum mapping, in this case, you've got a pure bias correction or adjustment. So in the literature until a couple of years ago, the term bias correction was in use, and now the IPCC, for example, uses bias adjustment. So, but yeah, it's really the same thing. Okay, and in this case here, when you map between your model output and the observations at the same scale, then you just have a pure bias correction or adjustment. And if you map your model output with station data, then you're implicitly also downscaling. And this may in some cases work well, but in some cases you might be really in trouble. Okay, now let's have a look at the performance of a bias adjustment method. And I will just very briefly rush over this. And you may find more detail in a couple of papers. So there was a European cost action. So that's a big European research network where people meet and talk to each other and define frameworks or whatever. And we had one running for evaluating statistical downscaling and bias adjustment methods and weather generators and every kind of statistical models you use to post-process climate model data. And we defined this framework, so you can read everything here in this publication on in Earth's Future. And then we conducted a very, very big exercise with something like 50 or 60 methods participating, and had a joint protocol, which was defined in this paper. And then we looked at the evaluation. And this is the synthesis paper of this evaluation, but it's a full special issue. So there are altogether something like 10 papers, which you can read to really learn about how different bias adjustment models perform under which conditions for which purpose. Okay, and I would just want to give a brief overview here. Yeah, and if you're really interested in, then you could go into these, in particular these papers here. I would say these are the most relevant then. So this is now for temperature. And what we did is we used, again, reanalysis data, purely reanalysis data. They are biased against observations, of course, and they have got a coarser resolution. And then we also used reanalysis, which was downscaled with an RCM. So that's this one here. And then we checked how well do these models adjust biases. And these are many, many different ones. So from the top to the bottom, it's increasing, let's say, complexity. So these are just additive methods. Some of these methods can also rescale the variance. And then here you've got really all the quantum mapping methods. And what we checked was how it corrects the mean, the variance. Here, this is the 20-year return level. The low end, and here the high end of the distribution. So this would be cold days, this would be hot days. Then the autocorrelation function. And this is lag 1 and this is lag 3. So this is a bit longer memory. And then the interannual variability. And here we had the longest wet spell, warm spell, then the amplitude of the seasonal cycle, and the phase of the seasonal cycle. So whether the peak and the minimum are correctly mapped. And then here it's the spatial correlation length. And every time you've got here one or let's say 5 within this block here, then the first is the annual result, and the other 4 is the seasonal result. So basically winter, spring, summer, and fall or autumn. Here we only have 1 per year, and here it's again annual and seasonal. So this is the spatial correlation length. So how fast does temperature dependence decay across space? And this is, again, up here, it's the raw data, the uncorrected reanalysis, and then here you see the performance. And basically all these things here are well adjusted by the bias adjustment methods. I mean, in many cases, you don't have any problems here. But you can also see that, for example, the interannual variance is not quite corrected. And what you can also see is that the spatial decorrelation length is not corrected. And Mathieu will talk a bit about this here, because you can define multivariate methods which may improve this at some cost. Okay, and here's the same for rainfall. Yeah, you see the reanalysis is much worse for rainfall because it's not assimilated into the data. So it's really a model product. And you see that many bias adjustment methods get many things better. But some things, depending on the method here, if they are too simple, they can't adjust, of course, the skewness, for example. So how much is the distribution tilted? Or really, if it's not designed to do anything about extreme events, then it can't adjust the extremes. And then here you've got interannual variability, and here the spatial correlation length. So this is also something they can't correlate. So if your model simulates 2 big weather systems, yeah, like a thunderstorm or a rainfall pattern, these will be, after bias adjustment, still be too large in spatial extent. And you should always keep this in mind. Okay. And well, these things here, of course, that they look so nice, in a way it's trivial because this is what the bias adjustment adjusts. So it's designed to do that. And if it doesn't do it, then it's badly designed. Okay, and now let's get to the challenges. And one thing I would like to discuss a bit is this bias adjustment and downscaling. So if you really use it for the downscaling purpose, so we are here on the right-hand side. Yeah. And the issue, so that's just conceptually about it. When your climate model simulates a certain value, it simulates an area average, let's say 25 by 25 kilometers. Or if you have a GCM, yeah, you may have 100 by 100 kilometers even. And then when you have got an observational station and you map between the two, yeah, then the same area average value can of course correspond to many, many local patterns. You could have light rain everywhere. You could have no rain somewhere and heavier rain over the other area. You might have a thunderstorm here, which misses the station. So the station records 0 rainfall. Or the thunderstorm sits really on the station and you record heavy rainfall. Yeah, this is all consistent, or might all be consistent with the output of your RCM. And so if you have a deterministic mapping, yeah, you can't represent that. And this is what I want to show you. So I looked into a certain region where we had many, many stations in Germany. So here in this RCM grid box area, we had more than 20 rain gauges. So basically the area, the average of these 20 something stations corresponds roughly to an area average over the region. And I applied quantum mapping separately to summer and winter. So each time series was adjusted, and I didn't even do a cross-validation. So the mapping was just perfect here. You see, this is before the correction, the red, and after the correction, it's blue. So the model is really perfect. And here, I basically show you the time series of the 20 stations here for just 2 arbitrary summers, because the problem is worst in summer. Yeah, you see, so basically, blue means high intensity and red means no rainfall at all. Okay, so and you see that you sometimes have, let's say, low rainfall intensities everywhere, or medium rainfall intensities, let's say. And sometimes you have thunderstorms, which are very, very heavy here, a bit less here, but you may have no rainfall at all in other places. Now, this is what an RCM simulates. It's not synchronous with this one here. It doesn't have to be synchronous. So don't try to, or don't believe that it's a problem that these don't match here, the rainfall events. But you see this RCM sometimes simulates high intensity rainfall. And because you apply the quantum mapping to each station, you basically get high intensity rainfall now everywhere. So instead of having localized thunderstorms, your thunderstorms basically happen everywhere in all the region. And this is what comes out now. When you take the area average of the rain falling in that grid box, then your extreme events, all the thunderstorms, they get blown up. They get about when you in reality have something like I don't know, 25 millimeters of area average, then you get something like 35 millimeters. So it's about a third, more than a third higher, the rainfall intensity. And also when it's dry, or when it's drizzle, then you might have in your model, then you might have some dry areas somewhere, but your model then may change the drizzle to no rain everywhere, so that you basically don't have any rainfall. So you basically have too many dry, fully dry days across the area. And if you want to use that to drive a hydrological model, yeah, which is distributed, then you run really into problems, because all these stations which you correct to, when the model simulates a thunderstorm, then it really blows up the rainfall, the total rainfall over the area. That means your runoff will be far too high in the end. Okay, so these two are the problems here. Okay, there's a similar problem, but it's maybe not so severe for temperature. So again, let's assume we've got some small variability within the grid box of the model. So here it's an GCM grid box. Then you can even have this problem for for temperature. So what I did is I took 2 stations in California, one in the Sierra Nevada, higher up, at, I don't know, 1,000 meters height, and one down in the Central Valley. And this is the temperature difference, the observed temperature difference between the two. So you typically have the station in the valley being warmer, yeah, on average 2 degrees warmer than the station higher up in the mountains. But sometimes you've got a temperature inversion. Yeah, so you may have a weather situation where basically you've got fog or low clouds, yeah, and then it's warm above and it's cool down. And the model doesn't resolve this because the model is too coarse. It doesn't distinguish between the valley and the mountain. So it doesn't represent this temperature inversion. And what you then get if you do a bias adjustment between these two, between the model output and the two stations, you basically get a very, very narrow difference between the two. So in case you use quantum mapping, if you just would do a mean adjustment, then the difference would always be exactly 2 here. So so in your bias adjustment data, you would never get a temperature inversion. And in some situations, yeah, if you're thinking about agriculture or so, this might be an issue. So I hope I could show you that using quantum mapping for downscaling might be, or any bias adjustment, might bring you into trouble. Less so with temperature, more so with rainfall. And so really be careful. So some authors really recommend, yeah, they say you don't need to downscale a GCM with an RCM because you can always do quantum mapping and then get to the low resolution you need. And I would say this is highly misleading. So what you can do is you can try to separate the two. So you may do a bias adjustment first on the same resolution with grid observations. And then afterwards, you can do a downscaling, really stochastic downscaling, which brings you to the point scale. So that would create local variability. And there's another issue why it's dangerous doing downscaling with bias adjustment. So let me just rush through this figure here. On the left, you see simulated present climate in the, well, let's say it's California and Sierra Nevada. So here, basically, you've got San Francisco, and this is the coastline here. So Los Angeles is somewhere down here. Okay, so you see the model simulates it's cooler here inland and it's warmer towards the sea. And this is what observations tell you. So you see high up in the mountains here in the Sierra Nevada, it's very, very cool. It's very warm in the Central Valley. And then here you've got the coastal mountain range, so it's also a bit cooler. And the high resolution RCM can simulate you this here. Yeah, so that looks really, really good. So you get the cool temperatures high up in the mountains, and you get the high temperatures here in the valley. So the RCM very much adds value to the GCM. Now, you could argue that you could do quantum mapping. Yeah, if you do a quantum mapping from here to the observations, then your GCM output, bias adjusted, would look perfectly like this one here. And you could say, hey, wow, I don't need to downscale. Yeah, but now let's have a look at the climate change signal. So here is the climate change signal of the GCM. It produces stronger warming over land, yeah, than over the sea. That's a typical thing. This is the signal after the bias adjustment. So the bias adjustment just adds some noisy pattern here. And this is the climate change signal from the RCM. And it basically tells you that it's much, much stronger, the climate change signal, in the high mountains. Well, it's the spring season we look at. So this is where you have got the snow melt. And where this snow albedo snow albedo feedback is very, very strong. So if the snow melts earlier, you've got the dark surface, which heats up stronger. So in spring, global warming in high altitudes is much stronger than in the valleys. And this is what the RCM simulates here. And by quantum mapping, you don't get there. So it looks perfectly fine in present climate, but it gives you the completely wrong climate change signal. We don't know whether this is true, but it's much more plausible than this just noisy thing here. Okay, so this is again a reason to include processes simulated by an RCM instead of just doing a simplistic quantum mapping. Yeah, I mean, if you're interested, for example, in the snow or in the forests high up there in the mountains, you get into trouble when you do just a quantum mapping. Now let's have a look at location biases. So here, what we did is we looked at the correlation at the seasonal scale between observations and an RCM, which is driven by reanalysis data. So on longer time scales, these should be synchronized. And you see, in particular in the coastal regions, the correlation between the two, between the observations and the model, is almost 1. Yeah. And in many regions, it's above 0.7. So I would say this is a really, really high correlation. But you see that in mountain regions here, the Alps and the Carpathians, the correlation is very low. It's below 0.3, and some regions is even below 0.1. And what we did then was we just searched for the highest correlation in an 11 by 11 grid box field and found always, in most regions at least here, for example, in the Alps, we found always another grid box which was shifted by, let's say, 50, 70, 100 kilometers, which had a much, much higher correlation with the observations, where the model output had a much higher correlation. So what that means is that your model basically, because the topography is very coarse still in such an RCM, basically simulates all the weather spatially displaced. So that means the weather, let's say, from the northern Alps in reality might get through to the southern Alps, but in the model it never gets to the southern Alps. So the weather divide in the model is much stronger than in reality. And if you're interested in the weather in a valley, then somewhere in the Alps, you might again get the wrong weather because the winter storms don't arrive there, for example. Yeah, whereas in reality they would do. Okay. Another issue is you can get to unrealistic climate change signals, or let's say physically implausible even. So here we have got two different models and GCMs on the top here. One, I don't tell you which one this is, and here in the bottom I tell you because it's the model of our hosts is it's the EC-Earth model, and here the white shading, that's the observed rainfall patterns. Okay, and the blue is the simulated rainfall patterns. So you see, oops, sorry. You see your model here has a spatial shift. The rainfall pattern is too far south. So basically that's this typical thing. The storm track in climate models is typically, it might be shifted to the south, and it doesn't go here really to the north, but it goes more towards Central Europe. That's a typical problem in climate models. So when you in this region here between the red lines, when you look at the present rainfall, you get this zonal average here. So this is 20 degrees latitude, this is 80 degrees latitude. You see the peak here in the observations is, sorry, in the model is somewhere at 45, yeah, which is completely unrealistic because in reality you've got the peak somewhere in Norway. Everybody has been to Bergen and knows that. The peak is roughly at 60 degrees north. Okay. And this is now the climate change signal your model simulates without correction. So the model shift simulates that the storm track and the rainfall patterns move northwards, yeah, from about, I don't know, 40 something here, more, let's say 2 degrees further north. And when you do the bias adjustment of the rainfall locally, this is what comes out. Your peak shifts to the south. So the storm track in your model moves northward, but the bias adjustment changes it to a southward shift. And that's because already in the uncorrected model, the peak is far towards the south. In the EC-Earth model, you don't have this problem because it doesn't have a location shift. So when you do a bias adjustment, you have to really take into account whether the model gets your circulation correct. If you have a circulation which is in the wrong location, then you will get artifacts. So you should always select wisely your models and don't think that bias adjustment can correct everything. And another issue, so this is location problems, but you may have also issues in the frequency of biases. Or when it comes to biases on specific weather types. So here, for example, this is from a paper of Nans Ador. It's a very nice paper. They looked into bias, and I just look at here westerly days, and this is biases overall in summer. So you take your climate model output and you do a bias adjustment for the whole summer. And then your bias, so the errors here mean basically for each model, it's a different color. And this is the bias before the adjustment, and this is the bias after the adjustment. And you see, you can basically remove all the biases. This is what your model is designed for, your bias adjustment. But when you look at the conditional biases, you look at the westerly days and the rainfall on these westerly days, then after the bias adjustment, you still have a bias. Yeah. And that's because your climate model may not correctly simulate the right frequency of westerly days. And if you do an overall collection, then it still cannot correct, of course, this frequency of the westerly days. And so that means westerly days typically may bring you more rain, yeah. And let's say easterly might be dry, yeah. Then you do an overall correction, which might even make things worse in some cases. Like for this model here, yeah, this here is the observation, yeah. It might even make things worse on these weather days, on these specific weather patterns. And here we did a similar study, but now for spell durations, yeah. If you do a bias adjustment which doesn't adjust the temporal structure, then you might argue that, well, it may adjust your individual values on each day, but it doesn't adjust, let's say, dry spells or hot spells, yeah, heat waves. And this is now for different models here. And here is the dry spell duration, and red means prior to bias adjustment, and blue means after the bias adjustment. This is for Austria. And here on the right-hand side, we see heat waves. And you see for the heat waves, basically, all the problems are gone, but not for the dry spells. Usually it gets better. In this case, it doesn't get better; it gets even worse. And this is linked to the fact that the dry spells are really defined very strongly by weather pattern persistence. And if that's wrong, then you can't make anything about it. Yeah, you can adjust the dry day frequency or the wet day frequency, but otherwise you don't get things much better. Final things I would like to talk, or how much time do I have left?
Well, if you could finish in about 5 to a few more minutes.
Yeah, that should be fine, I think. So what we did here was what I did actually, we had a look at how biases might change between present and future climate. And of course, we don't know future climate in reality yet. We have to wait. What we do is what I did is I used a so-called pseudo-reality. So I basically took 2 climate models. In fact, I chose 4 models, and then took one as a reality, and then I adjusted the other models in the present climate against that model, and then looked at how it works in the future. And now here's the present bias. So that's the mean across all model combinations in winter and here in summer. And this is the remaining future bias. And you see it has been much improved on average. But when you look at this is the mean improvement. And you see, usually it improves quite a lot, in particular in the regions where you had strong biases. But then, in particular here in summer, you may see that, and in winter, yeah, you may have the worst case improvement might actually not be an improvement, but bias adjustment may make things much worse, because some models really don't get, and I looked into this here, so for example, don't get the soil moisture temperature feedback correctly. And when you adjust that in present climate, you may get an even worse signal in the future. And this brings me to the last major thing. Standard quantum mapping modifies trends, and that's easy to understand when we just look at this here. So let's say this is what the model simulates, yeah, and this is the distribution. And now you do an adjustment because your model doesn't simulate the extremes well. So let's say it simulates too low high temperatures and too high low temperatures, yeah. So you broaden everything by quantum mapping, and then of course you change the trends, yeah. The trend gets stronger, and that's something which is intrinsic to standard quantum mapping. It modifies trends, and some people argue that this is an improvement. It basically improves the wrong trends. But I think there's growing understanding that this is a model artifact, and we don't simply know whether this is something useful or not. And problem that there are essentially two problems. One is more a statistical issue, and the other is a physical issue. But in the end, they are identical. So quantum mapping doesn't really distinguish between the force trend and the internal variability. And when you just want to adjust the internal variability, you typically adjust the force trends as well. So as a result of that, people have developed many trend-preserving variants of quantum mapping, and some are relatively simple. They just subtract the trend first, then do the quantum mapping, and then add the trend again. But other are much more sophisticated and really do the correction on all the different quantiles. And now the final thing, and that's a funny thing, but it's a rather deep and well, worrying thing, I would say. It's the way how you can adjust, how you can validate. And I'm sorry, my son starts crying a bit. I need to finish in a second, so I will just rush over this here. But you can read all of this in this paper here. So what we have done is we wanted to show that it's very difficult to evaluate whether a bias adjustment works, even in a cross-validation setting. So people say, well, you have to do cross-validation and then everything works out fine. So what we've done is we've basically done a bias adjustment of model output over Germany. And the model data which we took was not the rainfall over Germany, but we basically just took it from the other side of the planet, so somewhere close to New Zealand, the model rainfall there. So it has nothing to do on interannual variability. These trends might be very different with what we see in Germany. And so this is what the model simulates. Here is the 95th percentile, sorry, the mean, and down here is the 95th percentile. And this now is the observations, yeah, here and there. And you see it looks completely different, of course, yeah. Then, I mean, this is over the sea, so you don't even see any topography here, of course, because it's the Southern Ocean somewhere. And but when you bias adjust, then it perfectly matches this one. And you can say, well, yeah, that doesn't make sense. Who would do such a stupid thing? Yeah, well, you would identify this with a cross-validation. So we calibrated this over a calibration period, and then we looked at this over the validation period. And this is what comes out over the validation period. And still, it looks almost perfect. So here, when you look at the distribution of biases prior to the adjustment, you see it's completely off. And after the adjustment, it looks very, very good. And here it's even for the different quantiles, it still looks very good. So it's extremely difficult to identify whether a bias adjustment you did makes sense. And so if you want to evaluate a bias adjustment, you should always look into, for example, does it do anything harmful to the temperature, for the temporal dependence, or for the spatial dependence, the spell lengths, some things like that, yeah. If you see that this is still very, very different after the bias adjustment, then you know your bias adjustment was not very successful. So the long summary is bias adjustment is a pragmatic interface. It performs well with perfect predictors. That was this performance part. It cannot downscale. And it cannot adjust for location biases and for weather type frequency and persistent biases. It may be state dependent, and it may create artificial trends. And the evaluation is really challenging, so it's difficult to identify whether what your bias adjustment does is really something sensible. So the brief summary is all models are wrong, but some are useful. So the question you need to ask is not, is the model true, but is the model good enough for this particular application? So you really have to look into your climate models, whether they are good enough, whether they are adjustable. And I've shown you this with the location bias, for example, or with the frequency bias in the weather type frequencies. If these biases are very strong, you will not be able to correct that. And if you want to learn more about that, I would like to advertise my book here, which I've written together with Martin Wiedmann, who is also an expert on bias adjustment and statistical downscaling. And then some other literature. So the special issue I mentioned already, and the new IPCC chapter 10, where there's a lot about model performance. And this whole chapter is about how to build information which you can use for regional impact modeling, for decision making. And you have to really consider not only to choose a wise bias adjustment method, but you also have to consider whether your models, the climate models, are fit for purpose. And that's it, essentially. Thanks a lot.